Welcome to Credit Scoring in Python, Building a Complete Scorecard. This script is titled Credit Scoring in Python, Building a Complete Scorecard, describing the topic. This notebook will teach you how to develop a credit scorecard from start to finish using Python. Running the cell now. By the end of this lesson you will understand how to transform raw credit data into an analytical scorecard. First, import the core Python libraries used for analytics and visualization. This line is a comment indicating the import of libraries. We import the pandas library for data manipulation and analysis. We import NumPy for numerical operations and handling arrays. We import matplotlib.pyplot to create visualizations and plots. We import Seaborn for statistical data visualization built on matplotlib. We import train_test_split to split data into training and testing sets. We import logistic regression, a linear model used for classification tasks. We import metrics to evaluate model performance, including ROC, AUC, and confusion matrix. We import the warnings library and disable warning messages to keep output clean. We set Seaborn's theme as a white grid for a clean plotting style. We set the random seed of NumPy to 42 to ensure reproducible results. Running the cell now. This initial code block sets up the Python environment by importing essential libraries for data manipulation, visualization, modeling, and evaluation. Although there is no visible output, this step is crucial as it lays the foundation for building and validating the credit scorecard model in later sections. Notice how these imports align with typical steps in scorecard development, from data processing to logistic regression and performance metrics. The environment is now ready for credit scoring analytics. Let's load the accepted and rejected datasets. We start by loading the datasets. We read this accepted.csv file into a pandas data frame named accepted. We read the rejected.csv file into a pandas data frame named rejected. We print the shape, rows and columns of the accepted data frame. We print the shape, rows and columns of the rejected data frame. We print the list of column names in the accepted data frame. Running the cell now. This output highlights a file not found error, indicating that the accepted.csv file is missing from the working directory. This error stops the data loading step, which is crucial for building the credit scorecard because we need both accepted and rejected applicant data to model credit risk. Ensuring correct file paths and data availability is a key initial step before proceeding with scorecard development. Both datasets are now available for exploration. Here is the data dictionary for reference. This section provides a detailed description of each column in the dataset, explaining what each feature represents and the possible values it can take. Running the cell now. Understanding each variable's meaning helps guide feature selection and WOE for computation. We now infer a binary target variable for good and bad loans. Start by determining which column represents the target variable. Look for columns in accepted or that of names containing target or bad, ignoring case. Check if any such columns were found. If found, choose the first matching column as the target column. Create a binary target column where values like 1, bad, or bad are mapped to 1, else 0. If no suitable target column is found, proceed to create a synthetic target. Calculate total number of rows and set 20% of them as bad, 1. Create the target array with the specified bad rate and shuffle it. Assign this synthetic target array as the target column in the data frame. Display the normalized distribution of zeros and ones in the target column. Running the cell now. This output shows a name error because the data frame accepted hasn't been defined or loaded before running the target inference code. In this lesson section on the data dictionary, the intent is to identify or create a target variable by examining column names and values, but without the actual dataset, the code cannot execute properly. This error highlights the importance of ensuring your data is loaded and accessible before manipulating or analyzing it. A synthetic target column has been added to the accepted data. Let's inspect the dataset summary. We print the first few rows of the data frame to get a quick look at the data. We print the summary information of the data frame, including data types and non-null counts. We print the count of missing values in each column, sorted by the columns with the most missing values. Running the cell now. The error, name accepted is not defined, means the data frame named accepted hasn't been created or loaded yet, so the code can't display or analyze it. In this data dictionary lesson, it's crucial to first define and load your dataset to explore column info, sample data, and missing values before interpreting data structure. This step ensures you can understand the dataset shape, key columns, and completeness for effective analysis. We confirm numeric, categorical, and target variable distributions. Visualize missing values to quickly assess data completeness. We add a comment to explain that we are visualizing missing values with a heat map. We create a new figure with dimensions 10 by 4 inches for the plot. We generate a heat map showing where values are missing in that accepted data frame, without a color bar, using the Viridis color scheme. We add a title to the heat map to clarify what it represents. We rotate the x-axis labels 45 degrees and align them to the right for better readability. We display the heat map plot on the screen. We add a comment indicating that we will now summarize missing values. We calculate the total count of missing values per column in accepted. We filter to keep only columns with missing values, then sort them in descending order by the count of missing entries. We check if there are no missing values detected, empty result. If no missing values are present, we print a confirmation message saying so. Otherwise, we print a summary of columns along with their missing value counts. Running the cell now. The code intended to visualize and summarize missing values in that accepted a dataset to understand data completeness, a key step in the data dictionary section. However, the output shows a name error because that accepted data frame is not defined, so no heat map or missing value summary could be generated. This highlights the importance of properly loading or defining datasets before analysis to ensure accurate data inspection. The heat map and summary confirm whether missing values exist in the dataset. Let's visualize target balance. Plot the count of each class in the target variable using Seaborn's count plot. Set the title of the plot to good vs bad loan distribution. Set the label for the x-axis to indicate the target variable and its meaning. Set the label for the y-axis to count to show the frequency of each class. Display the plot on the screen. Running the cell now. The error, name accepted is not defined indicates that the data frame accepted has not been created or imported before this code runs. In this lesson's context, it's crucial to ensure you have loaded and understood your dataset, such as distinguishing loan outcomes labeled in the target column, before performing any visualizations like the count plot intended to show the distribution of good versus bad loans. This teaches us that setting up and referencing your data correctly is a vital first step in data analysis. Around 20% of loans are bad as expected. Perform a numeric summary for numeric variables. We compute describe statistics. Running the cell now. The name error indicates that the variables accepted hasn't been defined or loaded before calling .describe. This reminds us to always ensure our dataset is properly imported and assigned to a variable before exploring its structure. Defining the data is the crucial first step to accessing its key statistics and understanding the data dictionary. This overview helps spot outliers and ranges. Plot correlations among numeric features. Select the columns in the accepted data frame that contain numeric data types. Create a new figure for the plot with a size of 8 by 6 inches. Plot a heat map showing the correlation matrix of the selected numeric columns using the cool-warm color palette without annotations. Set the title of the plot as Correlation Heat Map, Numeric Features. Display the plot to the output. Running the cell now. The error name accepted is not defined indicates that the dataset accepted was not loaded or defined before this code ran. In this lesson on the data dictionary, the intention is to analyze numeric features by visualizing their correlations, but to do that successfully, we first need to ensure the dataset is properly imported and available in the workspace. This step is crucial to explore relationships between key numeric columns like loan amount or interest rate. Strong correlations indicate potential predictors for credit risk. Let's implement helper functions for weight of evidence, WOE, and information value, 4. Define a function named calc_o_ for that takes a data frame, a feature column name, and a target column name as inputs. Initialize an empty list to store WOE and IV calculations for each feature value. Iterate over each unique non-null value in the specified feature column of the data frame. Create a subset of the data frame containing only rows where the feature equals the current value. Count how many rows in the subset have the target value 0, good cases. Count how many rows in the subset have the target value 1, bad cases. Calculate the proportion of good cases for the current feature value relative to all good cases in the data frame. Calculate the proportion of bad cases for the current feature value relative to all bad cases in the data frame. Compute the weight of evidence, WOE, as the natural logarithm of the ratio of good to bad proportions, adding a small constant to avoid division by 0. Calculate the information value, for the current feature value using the difference in proportions times the WOE. Append a dictionary with the current value, its WOE, and IV to the list. Convert the list of dictionaries into a pandas data frame for easier analysis. Sum all the 4 values in the data frame to get the total for the feature. Return the data frame containing WOE and IV for each value, along with the total for the feature. Running the cell now. This code defines a function to calculate the weight of evidence, WOE, and information value, for a given feature relative to a binary target, which helps in understanding the predictive power of categorical variables. Although no output is shown here, the key takeaway is that the function breaks down the feature by unique values, compares distributions of target classes, good versus bad, and computes WOE and IV to quantify their separation. This aligns with the lesson's intent to build a data dictionary that includes metrics for feature evaluation before modeling. These metrics help rank variables by predictive power. Compute for categorical variables. Initialize an empty list to store for summary results. Identify categorical columns in the data frame accepted by selecting those with object dtype. Start a loop to iterate over each categorical column identified. Begin a try block to attempt to calculate WOE and IV for the current column. Call the function calc_o_4 with the data frame, current column, and target variable to get IV value. Append a tuple of the current column name and its IV value to the IV_ summary list. Handle any exceptions that occur during IV calculation by skipping the column. Create a data frame from IV_ summary with columns, a variable, and IV, then sort by IV in descending order. Display the top 10 rows of the IV summary data frame. Running the cell now. The output shows a name error because the data frame accepted has not been defined or loaded before running this code. This highlights the importance of having a properly prepared dataset to calculate information value for categorical features, which helps us understand each variable's predictive power for the target. Before performing IV calculations, ensure your data is loaded and cleaned as outlined in the data dictionary section. We display the top predictive variables. Visualize top variables by information value. Select the top 10 rows from the data frame IV_df and assign them to top_4. Create a horizontal bar plot using Seaborn with IV values on the x-axis and a variable names on the y-axis, using the blues_art color palette. Set the title of the plot as top variables by information value. Display the plot. Running the cell now. The error name IV_df is not defined indicates that the variable IV_df, which should contain the information value scores for variables, is missing or hasn't been created yet. This highlights the importance of preparing and understanding your data before visualization, as the lesson aims to show how to identify top predictors through their information value. Make sure to calculate all load for_df first to effectively explore the variable's predictive strength. Higher for indicates stronger predictive ability. Prepare data for logistic regression modeling by excluding any variable that leaks the target information. Remove any column that directly or indirectly encodes the target to prevent data leakage. Create a list of columns from accepted whose names contain target or bad, ignoring case. Select numeric columns from accepted excluding the target-like columns and convert to a list. Assign the features matrix X using the numeric columns from accepted. Assign the target vector Y from the target column in accepted. Split the data into training and validation sets with 30% validation size, stratifying by Y for balanced classes and using a fixed random state for reproducibility. Running the cell now. The error name accepted is not defined indicates that the data frame accepted has not been initialized or loaded yet before running this code. This code intends to prepare features by excluding any columns related to the target variable, then split the data into training and validation sets for modeling. To proceed, ensure the dataset accepted is properly loaded and defined earlier in the lesson. The dataset is now clean and split into training and validation sets without target leakage. Fit a logistic regression model as the base scorecard. We initialize a logistic regression model with a maximum of 1,000 iterations. We train the logistic regression model using the training data, x_train and y_train. We predict the probabilities of the positive class for the validation data using the trained model. We calculate and print the validation AUC score, rounded to 3 decimal places. Running the cell now. This error tells us that the training data, x_train, hasn't been defined before fitting the model, which is essential for training and validating in logistic regression. In the context of the data dictionary lesson, it highlights the importance of properly preparing and referencing your datasets before modeling. Always ensure your feature and target variables are loaded and correctly named to proceed with analysis. Model trained, we'll review performance next. Visualize ROC curve to evaluate discriminatory power. Calculate the false positive rate and true positive rate for the ROC curve using validation labels and predicted probabilities. Plot the ROC curve using the calculated false positive rate and true positive rate. Plot a diagonal dashed gray line representing a random classifier's performance. Set the plot title to ROC curve, validation data. Label the x-axis as false positive rate. Label the y-axis as true positive rate. Display the legend on the plot. Show the plot with all the elements. Running the cell now. This error indicates that the variable y_val, which should contain the true validation labels, is not defined in the current environment. In the context of the lesson on the data dictionary, this highlights the importance of correctly defining and referencing dataset components before using them in code, especially when calculating metrics like the ROC curve. To proceed, ensure y_val is properly loaded or assigned so the ROC curve can be generated to evaluate model performance. A smooth curve above the diagonal shows good discrimination. Plot decile-based lift chart. Create a data frame combining actual target values and predicted probabilities. Divide the predicted probabilities into 10 equal-sized groups, deciles, and assign labels from 0 to 9. Calculate the average target value, bad rate, for each decile, sorted from highest to lowest decile. Create a bar plot showing the bad rate for each decile. Set the title of the plot to a lift chart, by decile. Label the x-axis as the decile, high score low. Label the y-axis as the bad rate. Display the plot. Running the cell now. The error indicates that the variable y_val is not defined before running this code, which is essential because y_val represents the actual target values and y_pred_prob the predicted probabilities. This lesson section emphasizes understanding the data dictionary and ensuring all key variables are correctly initialized and available before analysis. Fixing this will allow us to observe the lift chart, which shows the bad rate across score deciles, helping gauge model performance by comparing predicted risk groups. High lift in early deciles indicates good risk separation. Now that we have an initial scorecard, we'll apply reject inference. We estimate the behavior of rejected applicants by assigning probabilistic weights derived from model scores, a method known as reject inference using the fuzzy method. Running the cell now. This adjusts for missing outcomes among rejected applicants. Align the rejected dataset so its features match the training structure before scoring. Align the rejected dataset columns to match those used in model training. Identify the columns available in both the training data and the rejected dataset. Identify the columns present in the training data but missing from the rejected dataset. Create a copy of the rejected dataset only with columns common to both datasets. For each missing column, add it to the rejected data with a default fill value of 0. Reorder the columns in the rejected data to match the exact order of the training features. Use the trained model to predict the probability of the positive class on the aligned rejected data. Show the first few predicted probabilities to verify the results. Running the cell now. The error here highlights that the variable x_train is not defined in the current environment, which prevents aligning the rejected dataset's features with the training data. This step is crucial because the fuzzy reject inference method requires the rejected samples to have the same feature set and order as the data used to train the model. Without x_train, the code can't ensure compatibility for prediction, so defining or loading x_train is essential before scoring the rejected data. Predicted probabilities have been generated for rejected applicants, ready for fuzzy augmentation. Apply fuzzy augmentation to combine accepts and rejects. Set the rejection rate to 0.3. Create a copy of rejected_scored for fuzzy good cases, setting target to 0 and weight based on rejection rate and inverted predicted probability. Create a copy of rejected_scored for fuzzy bad cases, setting target to 1 and weight based on rejection rate and predicted probability. Combine accepted data with fuzzy good and fuzzy bad samples, assigning weight equals 1 to accepted, to form the augmented dataset. Print the size of the augmented dataset. Running the cell now. The error here indicates that the variable rejected_scored is not defined in the current environment, which stops the code from running. This step is crucial in the reject inference lesson, as rejected_scored should contain the rejected applicants with their predicted probabilities used to create weighted fuzzy copies labeled as good and bad. Defining or loading rejected_scored properly is necessary to augment the dataset and proceed with this inference method. The augmented dataset is ready for final scorecard development. Train the final logistic regression model using the augmented dataset. Select feature columns from the augmented dataset to use as inputs. Extract the target variable from the augmented dataset. Get the weights column if it exists, otherwise use an array of ones. Initialize a logistic regression model with a maximum of 1000 iterations. Train the logistic regression model using the features, target, and sample weights. Print a confirmation that the model is trained and display the number of coefficients. Running the cell now. This error indicates that the variable augmented has not been defined or loaded before fitting the final logistic regression model, which is critical in the reject inference, fuzzy method, step. In this lesson section, it's important to ensure that the augmented dataset, combining labeled and inferred data, is properly prepared and accessible, as the model relies on it along with sample weights to improve classification by including rejected cases. Without augmented, the model cannot be trained, highlighting the need to carefully set up your data before this stage. The final model is now ready for score scaling and evaluation. Generate predicted probabilities for the augmented data. We calculate predicted probabilities and attach them to the dataset. We display the first few rows of the predicted probabilities and the actual target values. Running the cell now. The error here indicates that final underscore model hasn't been defined before making predictions, so the code can't generate predicted probabilities. In the context of reject inference using the fuzzy method, this shows the importance of ensuring the predictive model is properly trained and available before augmenting the dataset with prediction scores. Fixing this is crucial before analyzing how the model assigns risk probabilities to originally rejected cases. These probabilities will be converted into interpretable credit scores next. Now scale predicted probabilities into scorecard points. Set the base score points to 600. Define the points to double the odds, PDO, as 20. Set the initial odds ratio to 30. Calculate the scaling factor using PDO divided by the natural log of 2. Calculate the offset based on base points and scaled log of odds. Compute the score for each record by applying the offset minus factor times the model's decision function on augmented features. Display the first few rows of the computed scores alongside the target variable. Running the cell now. The error here indicates that final underscore model has not been defined before this scoring step, which is crucial because the code relies on the model's decision function to calculate credit scores. In the context of reject inference using the fuzzy method, defining and fitting the model on augmented data must precede scoring to produce meaningful probability-based scores. Fixing this will allow you to see the score column aligned with target, showing how inferred rejects impact your score distribution. Scores are now on an interpretable 300 to 900 range. Visualize the score distribution for good vs bad loans. We create a histogram of the score variable, separated by her target categories, with kernel density estimation overlaid and a color palette applied. We set the plot's title to Score Distribution by Loan Outcome. We label the x-axis as Credit Score. We label the y-axis as Account. We display the plot to the output. Running the cell now. The error, name augmented is not defined indicates that the dataset intended for visualization, which should contain the augmented scores, is missing or not yet created at this step. This highlights the importance of properly generating or loading the augmented data before plotting, as the reject inference, fuzzy method, lesson aims to compare score distributions by loan outcome to understand how rejected applicants are inferred. Fixing this will allow us to visually examine how the score distributions differ between accepted and rejected loans. We expect bad loans to cluster at lower scores. Compute validation ROC and KS statistics for the final model. Generate the predicted probabilities for the positive class on the validation set. Calculate the area under the ROC curve, AUC, to measure model performance. Compute the false positive rate, FPR, true positive rate, TPR, and thresholds for the ROC curve. Calculate the KS statistic by finding the maximum difference between TPR and FPR. Print the AUC and KS values with 3 decimal places of precision. Plot the ROC curve with a label displaying the AUC value. Plot a dashed diagonal line representing a random classifier's performance. Set the title of the plot to final ROC curve. Label the x-axis as false positive rate. Label the y-axis as true positive rate. Display the legend on the plot. Show the ROC curve plot. Running the cell now. The output shows a name error because the variable final underscore model hasn't been defined or loaded before this code block. In the context of the reject inference, fuzzy method, lesson, this highlights the importance of ensuring your trained model is properly assigned and accessible before evaluating metrics like AUC and KS or plotting the ROC curve. This step is crucial for accurately measuring the predictive performance of your final model on the validation set. AUC greater than 0.7 and KS greater than 0.3 indicate a solid scorecard. Plot average bad rate by score decile. Divide the score column into 10 equal-sized bins, deciles, and assign each row a decile label. Group the data by these deciles and calculate the average target value within each decile, then sort deciles in descending order. Create a bar plot of the averaged target values for each decile, using a cool to warm color palette. Set the title of the plot to describe what it shows. Label the x-axis to indicate the score deciles from high to low risk. Label the y-axis to indicate the average bad rate. Display the plot on the screen. Running the cell now. The error name augmented is not defined indicates that the data frame augmented was not created or loaded before this code ran. This suggests a missing step in the reject inference process where the original data should have been merged or augmented with inferred labels. Without augmented, we cannot group by score deciles to analyze the average bad rate, which is key to validating the fuzzy method's effectiveness in estimating risk across score segments. Higher separation means stronger discriminatory power.
Let us recap what we achieved.
Lesson recap. In this lesson, you learned to load and clean accepted and rejected loan datasets using pandas. Understand dataset structure through a clear data dictionary. Compute weight of evidence, WOE, and information value, to evaluate variable predictive power. Train a logistic regression model to build a base credit scorecard. Visualize model performance using ROC, KS, and lift charts. Apply reject inference to account for missing target labels among rejected applicants. Rebuild the model with augmented data for improved calibration. Scale model outputs into interpretable credit scores using base points, PDO, and odds. Plot score distributions to compare good and bad applicants. This workflow demonstrates how data analytics, model building, and interpretability come together to create a complete credit scoring solution in Python. Running the cell now. You have completed a full credit scoring project from data to deployment. Finally, here is a creative challenge to deepen your understanding. Creative challenge. Try extending your scorecard with the following ideas. Implement quantile-based or optimal binning for continuous variables using opt-binning or scorecard pie. Compare logistic regression with XGBoost, LightGBM, or CapBoost to evaluate non-linear effects. Use information value thresholds such as for greater than 0.02 for feature selection. Automate score scaling for different PDO values such as 15, 20, and 25 and visualize score shifts. Build a score to odds calibration chart for interpretability. Deploy your final scorecard as a REST API using Flask or Fast API to score new applicants dynamically. Continue improving your workflow and test on new data. Each iteration builds confidence and accuracy in credit risk modeling. Running the cell now. Exploring these extensions will strengthen your practical modeling skills.